All right, so today we're going to be talking about electric vehicle drivetrains, and actually all vehicle drivetrains or most vehicle drivetrains, not just EVs. I think the sort of best thing to do is to also learn a little bit about how gas cars work as well. So here we go. All right, how does a gas car work? So we're just going to walk through all the components of a gas car drivetrain so that we can see a lot of the sort of comparative differences with electric vehicles. Okay. So some of the grad students in here probably have seen this already, but that's all right. So this is a sort of typical four-stroke engine. So this is just one piston of the engine, and the four-stroke refers to sort of these four stages. So here you can see this piston kind of moving up and down. So what exactly is happening as we move through these? So in the first stroke, there are these intake valves here that essentially suck air into the cylinder, okay? And at the same time, so that's kind of being shown in this like blue that's getting sucked into this chamber here. At the same time, there is a fuel injector here that is aspirating fuel, your gasoline and the sort of fine particulate mist into the piston as well. So you've got your fuel air mixture in here. And so the reason why you need to do this, right, is because when you do combustion, you need to have oxygen present for combustion to occur. Okay, so it's using oxygen sort of in the atmosphere as part of the fuel air mixture. So that's happening during the downstroke. Okay, in the second phase, in this yellow, is a compression phase where the piston moves up. Okay, and so what happens there is all the valves are closed, so nothing can escape. And then the valve moves up, which pressurizes your fuel air mixture. The compression basically allows for a more sort of efficient and complete combustion to occur. In the third stage, this is where you're extracting energy and work out of this cycle. So after the second one, as it compresses, you have this thing here in the middle, which is a spark plug. And what that does is it will ignite that fuel air mixture, okay? And so when you sort of explode that gasoline inside this chamber, that creates work which will push the piston down, okay? And so all of the work is coming out of this third phase. And then in the last stage, the piston moves back up and there's a valve that opens up here. And the exhaust of your combustion byproducts get sucked out of your piston. Okay, and so this is basically how most gas engines work. Okay, and so as this piston kind of moves up and down, you have this connected to via a connecting rod to this shaft that's in the middle that we'll see in just a second. All right, any questions about this? Pretty straightforward. Okay, so we can see that in an engine, you're going to typically have more than one piston, right? And so you can see here that each of these four pistons are operating to rotate this crankshaft that I was talking about. And you can see here how some of the timing components that I was discussing in those four strokes happen at the correct time, right? So this thing is happening extremely quickly, right? And so you have to open up the valve, you have to ignite the spark plug, you have to open up the exhaust valve all at the right time. And the way that that happens is actually in sort of an analog way, right? So this the rotation of this crankshaft is connected to a timing belt here, which is then connected to this, which is known as a camshaft. And you can see here, the cams are oriented in such a way that they will physically essentially move these to open up the valves for the pistons at exactly the right time. And so you can't really physically have these operating at the wrong times. Okay, so if you look at your at the dash of your vehicle and you see that thing that's measuring the RPMs, this is what it's referring to. Okay, so RPMs is revolutions per minute. This is how fast essentially this thing rotates in a given minute. So usually you're operating between like 1,000 up to 6,000, 7,000, 8,000 RPM for your engine. Okay, any questions about this? So if you guys have ever heard of like a V6, V8, V12 engine, so the V refers to the configuration of the pistons. They'll be oriented in kind of this V shape, and the number refers to the number of pistons. So if you can imagine, essentially the more pistons that you have, this kind of smoother the action of the engine is. The sort of analog that I like to describe this at is if you imagine you're biking, right, with your pedal, and you think about the strokes that you're making, think about how jerky your bike would be if you only had one pedal, right? You'd have to like push really hard, and then you'd have to wait for the pedal to come back up, then you push really hard again, and that's like a sort of jerky motion. So as we add more pedals or sort of more pistons, that kind of smooths out the sort of delivery of power into your system. Okay. So other parts of the engine system. So I mentioned before, so the fuel injectors spray gasoline into the cylinders of your pistons at precisely the right moment. So this part is timed in a sort of precise manner. Does anyone know what fuel injectors replaced? Carburetors, yeah, exactly. So carburetors are more of a kind of analog or sort of manual way of getting fuel into the cylinders, where essentially you use airflow and you would kind of drip the gasoline in. It's a lot less efficient than using these fuel injectors. Okay, so before there's a question in a previous lecture about these octane ratings. So 87, 89, 93, right? You guys have all seen this. If you go to a gas station, what do these mean? So the octane rating, basically, so from a chemistry perspective, it typically means you have a higher ratio of octane molecules as opposed to heptane molecules in your gasoline. And effectively what that means is that it will resist something known as autoignition. Okay, and so that means the fuel mixture is less likely to combust under heat and pressure. So when you have higher ratings, right, you are less likely to have this phenomenon occur, autoignition. And so what autoignition does is actually, if we go back to the first slide over here, so you can imagine I'm going through my 4 strokes, and that cylinder is going to get really hot, right? As you operate your engine, especially if you decide to like throw down on the pedal and really sort of hit the gas, right? You're trying to go faster. You're working your engine harder. And so if this gets hot enough, you can inject the fuel in, and then in the compression stroke, it's hot enough where it'll ignite the fuel without the spark plug. So now you have your power stroke kind of happening when you have your compression stroke. And that's known as knocking. Not good for the engine, obviously. And so having higher octane rating gasoline will prevent that. So then, okay, should you always be buying this? Probably not. So most of the time, that type of phenomenon only occurs if you have vehicles with like really powerful engines. Typically, sort of higher end luxury vehicles and sport cars are really the only things that would need to do these higher octane ratings. Yeah.
So is it more expensive because the higher ratio of the octane and the fuel is more expensive to produce that kind of product? Or?
Yeah, exactly. So I guess octane, okay, I'm not gonna say I'm like 100% sure on this, but I think octane, I guess, is just slightly more expensive. And so I guess adding heptane is a way of making the fuel a little bit cheaper. Yeah. Any other questions? Okay. Okay, so as I was mentioning, combustion requires quite a bit of oxygen. Okay, and so the ratio is about 1 to 14 for each part gasoline requires 14 parts oxygen, right? You're going from C7, C8 to CO2. So for each molecule, right, you need 7 or 8 parts oxygen. So if you have a car on a 20-gallon tank, your engine will take in about 20,000 cubic feet of oxygen. That's quite a bit, right? And you have to imagine that all of that is getting converted to, or most of that will be getting converted to carbon dioxide, which is exacerbating some of the environmental issues with climate change. Oil, why do you need to get oil changes? So oil is used to lubricate the different parts of your engine. Keeps it clean, prevents corrosion, improves sealing, and actually helps cool the engine by heat transfer. And so it's usually a good idea to improve the lifetime of your vehicle's engine by having regular oil changes. Yeah, and not everyone does that. Not everyone does that regularly, but typically it's a good practice to have. Cooling. So this is an important aspect of, again, sort of making sure that your vehicle's drivetrain is sort of well maintained. If you keep it running at sort of higher temperatures, typically that means accelerated degradation. And we're gonna find kind of a similar principle even in electric vehicles, even though you're not cooling the engine. We'll talk a little bit later about how cooling of the battery pack has become an important issue over the last decade. So there's a couple ways you can, a couple different ways that they use to essentially help cool the engine. So radiator and a fan. So the radiator is basically a whole bunch of these like metal tubes, and you can have coolant sort of passing through these tubes in order to help keep it cool. And you have air flowing through the radiator to sort of pull the heat out as well. Also, you don't want to getting it too cold, so you have antifreeze. So that'll be a mixture of coolants and water. And basically, you want to be sort of maintaining your engine temperature within some kind of range. And you can see the sort of properties of water versus some of the coolant mixtures, which is why you use these, because it allows for sort of a wider range. Okay, some of the electrical components. So all of these things are essentially going to be powered through a onboard battery in your vehicle. So this isn't like the battery in an electric vehicle. These are your sort of clunky old lead acid batteries. Most vehicles will still have these. Actually, even some electric vehicles still use these clunky batteries. And these can be powered with an alternator, which works just like a generator, which we'll talk a lot about today. And so that's one way that you can help charge the battery, right? So that you don't need to like plug in your gas car. And so this helps to power a bunch of the onboard electronics. So things like your radio and stuff in your dash, as well as providing power for things like your spark plugs. Okay, and the last bit of the drivetrain, although technically, right, it doesn't actually help with any part of the propulsion of the vehicle, but this is important for other aspects. So the exhaust sucks out all of the combustion byproducts and passes through a catalytic converter. So when you combust gasoline, you're not always going to get sort of perfectly just CO2. There can be other sort of byproducts within the combustion mixture. You might have incomplete combustion, so you might still have some gasoline molecules. You could have other byproducts of incomplete combustion. A common one is like carbon monoxide, right? That's the whole thing. If you like run your engine in the garage, like people were, that could actually be dangerous because you could have a buildup of carbon monoxide. And you have a lot of nitrogen, right, in the atmosphere. And so that can lead to certain types of byproducts such as NOx. You'll get more of that in things like diesel combustion, but still sort of present. So the catalytic converter helps to reduce some of those toxic chemicals and pollutants. And then lastly, you've got a muffler, which reduces the engine noise. Yeah.
You were talking about diesel. I was wondering if you about depth fluid and
Wow, what is it called?
depth fluid. It's like a diesel exhaust fluid.
Oh, I am not an expert in heavy duty stuff, so I don't know the answer to that, but we will have some experts in heavy duty trucks coming as a guest lecture, so you can ask them then. I should also mention really quickly down here. Okay, so or sort of downstream, sorry, of this engine, this sort of mechanical energy eventually goes through the wheels through a sort of transmission system. And that transmission system is essentially a complex series of gears that basically translate the RPMs and rotation of your crankshaft into rotation of your wheels that you want going at a certain speed, right? We don't want our wheels rotating at like 3,000 RPM. That would be too much. And so this essentially like bicycle gears, right, helps to translate rotation to a different speed. And if we step back and we think about sort of the way that this operates, right, it's actually a little crazy. You're just taking these fuel and you're just like, over the lifetime of a vehicle, you're just blowing up fuel inside of these like metal containers and then translating that to energy to move your car. And there's a lot of moving parts, right? If anything breaks, you're basically done for, right? So your piston, your crankshaft, your timing belt, your camshaft, the transmission, all of these sort of moving pieces means that from a mechanical standpoint, there are lots of opportunities for failure. And so we'll see how that really sort of contrasts with the number of moving parts that you would see in like an electric vehicle. Okay. So any questions about gas cars before we move on? Okay. Okay, so we've seen this diagram before. For electric vehicles, one of the things that I wanted to highlight is that there is substantially fewer moving components, right? Really, the only thing that's moving is when you have your electricity from your battery pack that goes into an electric motor. And that motor is the thing that generates rotational energy that goes into your drive shaft that spins the wheels, and that's it, right? As opposed to all of those moving parts that we just described in a gas car. And so even from like a maintenance perspective, electric vehicles have been found to be way cheaper than gas cars. Yeah, so then for the fueling part, right, you no longer have a gas tank and you no longer have a fueling port. Now you have the charging port and your battery. And the other sort of big change is that with these vehicles, there are no combustion byproducts, so you don't need a tailpipe. So all that assembly is sort of gone. And all of that will help save space, right? You don't need the catalytic converter. You don't need a muffler as well. One of the sort of side effects of this is that vehicle weight is increasing. So you can even see in sort of the electric versus gas versions of comparable vehicles, you can see sort of how much heavier the electric vehicle versions are. And despite the fact that they don't have an engine, they now have these sort of big motors. But more importantly, the batteries are a fairly sort of substantial size and add quite a bit of weight. And that has sort of pros and cons. This particular figure is actually coming from this pretty high profile paper that came out in Nature last year, I believe. And one of the arguments is that there isn't that much sort of policy and regulation that's focused on efficiency for electric vehicles right now. And so, just because that there is zero emission sort of at the tailpipe, that doesn't mean we should sort of totally forget about conversations about efficiency regarding electric vehicles. There are some benefits though. So one of the arguments is sort of the correlation between safety and weight. Electric vehicles tend to do way better on safety tests. So for example, the Department of Transportation in the United States, they have a sort of sub-agency called the National Highway Traffic and Safety Administration, NHTSA, and they do all the testing for safety ratings for vehicles. And when the first Tesla came out, there's this test where you corner the vehicle at high speeds to try and flip it. But almost no matter how fast they went, they couldn't flip the car. And so they had to come up with a sort of different way of doing this. And Teslas tend to for example, rate at the sort of highest safety levels on their tests. And that's because they're so heavy. The batteries sort of sit in the bed of the vehicle, which means you have a really low center of gravity. And so for a lot of metrics of safety, they tend to score very high. Heavier vehicles tend to have less fatalities and a reduction in morbidity. But I will say that these things are not always that straightforward, okay? So one of the biggest reasons for that is fatalities. A lot of the mortality figures related to car accidents are vehicle-on-vehicle collisions. And that's almost always a function of the difference in weight between two vehicles. And so if two cars hit each other, the heavier car, like just if you think about this from a physics perspective, right, the heavier car is almost always going to win. And so if you are creating a differential in vehicle weights, like if you have a bunch of lighter gas cars and heavy electric cars, that can be problematic. Or if you have lots of people in trucks versus lots of people in sort of small cars, that can also be problematic. So there is some kind of like nuance to this where it's not just electric vehicles are safer because they're heavier. Kind of the ecosystem in which these vehicles are operating is really important as well. Yeah, but generally you can see fatality rate, how that sort of decreases as your vehicle gets heavier and heavier. Okay, any questions? All right, so back to the drivetrain. As I was mentioning, electric vehicles are extraordinarily simple. So you've got your engine here. It's a 100-year-old technology that precisely mixes all this fuel and air to this ratio. And then, you have all these pistons moving down. That transfers all this energy into this crankshaft to rotate your wheels eventually. And then in an electric car, you just have some spinning magnets. Great. Okay, so how the heck does that work? So if folks have taken E&M, this is sort of the basics. We're not going to get into like physics or sort of engineering concepts of the motor, but I will provide sort of a qualitative overview. So Faraday's law of induction, this is also known as Faraday's law. So if you have an electric current going through a coil, you can produce a sort of magnetic field. And conversely, a magnetic field can produce an electric current. So the way that we take advantage of this is you send a current through a coil to produce these magnetic fields that cause the coil to rotate in the presence of an external magnetic field. Okay, I have this little sort of handheld generator over here that you can see. So basically, the whole idea is that if I can cause something to spin, I can make electricity. Okay, so I can go like this, and yay, I produce some light, right? It's a pretty simple concept, but actually this is responsible for almost all of the electricity that we produce in the world. Okay, so if you're talking about a coal plant, a gas plant, a wind turbine, a hydropower plant, all of these things do the same work in the same way. Oh, I see a question back there. Or not. Okay, so those all operate by rotating essentially causing turbines to rotate to generate electricity. And those are known as generators. And if you cause these things to spin, then so if you're spinning the coil, right, the electric current gets induced that causes electrons to flow through your wires. So that question that I had at the beginning, do electric cars have generators or do they have motors? They all have both, because motors are just generators in reverse. Okay, they're basically exactly the same thing. If you're moving the thing, if you're providing energy to move the object, you produce electricity. And if you are providing electricity to move an object, then that becomes the motor. Okay. Any questions about that? Hopefully this is just kind of a review of some E&M, if folks have taken that. So, okay. There's two types of sort of electrical power that we'll be talking about. You've got alternating current versus DC, which is direct current. So on the left-hand side, we have direct current. On the right-hand side, we have alternating current. So the way that I like to kind of describe this is that, okay, suppose from an analogy of like water, suppose your energy is stored up in a water tower and you kind of open a pipe, right? How does the water flow through? Is it? Yeah, it's continuous, right? You can imagine that like the pressure is putting this continuous sort of force on the water, which is pushing that through the pipe. And so you should have like a continuous stream of water if you're using something like gravity to sort of push it down. Has anyone ever pumped a well before? Yeah, so what happens when you're like pumping the well? Yeah. Yeah, it essentially comes in these like bursts, right? So that's essentially what's happening with AC. And so I can demonstrate this. Hopefully everyone can see. So all of the electricity that we get from spinning things generates electricity via alternating current. And so if I sort of rotate this at a constant speed, you should see the light light up and then dim, light up and then dim, right? And that is this sort of thing happening where as I sort of rotate through the magnetic field, the way that the current, the way that the magnetic fields are lining up in my generator leads to you having sort of positive and negative voltage in this pattern. If you spin this fast enough, it'll look continuous, right? But that's just because it's kind of going faster than the eye can see the sort of light flickering in and out. Okay, and so the way that we get direct current, so this would be something from like a battery, also solar power actually operates in with direct current. So that solar power doesn't have anything spinning. It's sunlight that causes electrons to sort of get perturbed and move through a circuit. But there isn't this sort of feature happening. All right, any confusions about AC versus DC? So when you supply a motor with electricity, you need to have a specific type of motor to be able to handle alternating current versus direct current. You can imagine that if you think about kind of the electricity sort of moving into a motor, you can design one that's specifically built to handle electricity coming in this sort of continuous pattern versus coming in like this. Okay. And so again, we're not going to get into the sort of specific sort of engineering aspects of DC motors, but I'll just talk about these at sort of a high level. There's two basic types of DC motors. You've got brushed and brushless motors, and that refers to the configuration of essentially how you pass electricity to certain parts of the motor. The attributes of these motors, typically you have better speed control and output range. So sort of being able to tune a motor to sort of rotate at a specific speed, and the sort of range of speeds that you can rotate that motor tend to be sort of generally better with DC motors. So some electric vehicles do have DC motors. So the Nissan Leaf and the Chevy Bolt both use DC motors. So that's in contrast to alternating current motors. So there's two types of motors. So one is synchronous and one is known as induction. Again, this is kind of a high level generalization. So synchronous means that the rate at which the motor rotates is the same frequency as the electricity that's being supplied into the motor. So that sort of sinusoidal wave, the rotation of the motor will sort of mirror that. Induction AC motors use a sort of stator that's a sort of piece of the motor that basically stays still, and you use electromagnetic induction to create rotation. These motors typically have higher power output and efficiency compared to the DC motors, but they're not going to have, generally, they won't have as good sort of control over the speed. So Teslas use AC motors, sort of an advanced form of the induction motors. Yeah, and so motor technologies have actually come quite a long way in the last decade, especially as more and more automakers are sort of getting into producing electric vehicles. And even sort of 5 or 6 years ago, I think Tesla had really done a lot of innovative stuff in the technology realm for motors. They were kind of, I want to say, kind of like light years ahead of most other automakers. But I think a lot of them are sort of catching up now. Just to give you an example, so Tesla uses what are known as IPM, SYN, RM electric motors. So IPM is internal permanent magnet. So they like cut these slots into the motors and they put permanent magnets into there. And that helps with certain aspects of the motor operation. So like one of the things, let me see, actually here. Why don't you grab this? So give it a, rotate it quickly, faster, faster, faster. And do you feel, what do you feel happening as you go faster and faster? Yeah, oh, well, not with your wrist, but with the, do you get any like, does it feel harder than if you go slow?
Yeah, it's like it's harder.
Yeah, so there's this resistance that's happening. So the faster you go, and this is known as back EMF, and it's basically, you know, you're kind of operating this as a motor, but there's a generator portion of it as well that's kind of essentially as you increase in voltage, it's gonna kind of resist what you're doing. And so this is really relevant to like vehicle motors. If you go faster and faster, you'll start to get this resistance feedback, right? And so they discovered ways of essentially getting around that very creatively by having these permanent magnets create magnetic fields in such a way that it reduces the effect of like back EMF. And so this is all like sort of really cutting edge technology that really makes these motors quite a bit more efficient than their competitors, although people, right, are now sort of catching on to these things. Yeah, and so SYN-RM stands for synchronous reluctance motors. Okay, any questions about these motors? Great, okay, so for electric vehicles, are we operating in the DC world? Are we operating in the AC world? Okay, well, there are a whole bunch of things to sort of keep in mind here. So from the aspect of the electricity system, and this is something that will kind of go way more into detail later on in the class, but just for now, as I was mentioning, so the vast majority of electricity production, especially if you're talking about fossil fuel combustion or nuclear, and for wind, those all, the name of the game is make something spin to make electricity. So those all produce AC power. The only exception, or the main exception, is going to be solar, which produces DC, and they will have some kind of converter that goes DC to AC to make sure that it aligns with the rest of the electricity system. And so as you move through your transmission system and your distribution system, so transmission are like the really big metal towers that you see like off the freeway, and then the distribution lines are the sort of like the wooden poles that you see in local neighborhoods. All of those are carrying electricity at different voltages, but they're all carrying them in alternating currents. Okay, and so all of this will like go to your home, or these will go to like charging stations, right? You have like a transformer and a panel wiring for all this. And then we've talked about two different types of charging. You've got DC fast charging and you have AC charging. So this is out of the plugs out of your home. If you just plug your vehicle into this, then it will go through the onboard charger and there will be an AC to DC conversion. Okay, and why do we do that? It's because all batteries operate in DC, not in AC. And so if you plug your vehicle into your sort of typical wall outlet or your dryer outlet, that all gets converted into DC before it goes into your battery. And then if you're at a DC fast charging station, this can go kind of directly into your battery pack. Yeah. So it's, I guess the way that I would characterize it is that it's easier to operate sort of at higher voltages for DC. I mean, you can do higher voltage AC, but it's also a matter of cost, because the kind of equipment that you would need to like put into your vehicle to do that is probably going to be a little bit more expensive. And because the battery is in DC, there's like a natural preference, right, to having that sort of converter outside of the car. Yeah, from an economics perspective, you can think about it this way. This DC fast charger can service like many vehicles, right? And so you only need one converter to service, you know, however many vehicles charge at that DC fast charger, versus a world where you would have a converter basically in every single car. There is actually a DC AC converter in most electric vehicles anyways, but these are kind of operating in the sort of operational ranges within the vehicle as opposed to on the grid. So the battery pack will feed the motor, and if it goes DC, if it's a DC motor, you don't need this specific type of converter. You might still need some kind of converter and controller, right? If you want to mess with the voltages. But if you are going from your DC battery pack to an AC motor, like with a Tesla, then you do need a DC AC converter. Yeah, sure.
How feasible is it to have DC solar panels?
Yep.
How feasible is it to slap one on the roof?
Yeah. So that is a common thing that people talk about. But the thing you have to keep in mind is that, yeah, we could do, okay, let's do a quick sort of math problem here. So if you have, I think the number is about 375 watts per square meter. Yeah, so people can correct me if I'm mistaken here, but this is essentially the amount of irradiance energy that you can get from the sun. Okay, to the average sort of surface on Earth, it's about 375 watts per meter squared. A solar panel is about, let's say 20% efficient. Okay, so 0.2 times 375. Math. What is it? Yeah, 0.2 times 375, 75. Okay, yes. Doing math off the top of my head. Not the best. Okay, so 75 watts per meter squared. So if you put solar panels, this is about how much energy you could get. So let's say a car generously will probably have like, let's say we'll give it 3 square meters. Okay, so times 3, 225 watts. And so in 1 hour, okay, so 225 watts. So I can get 225 or 0.225 kilowatt hours per hour. Okay, so if I have solar panels on my car and I let it sit in the sunlight, and I had a really good system, right, at 20% efficiency, I get 0.225 kilowatt hours per hour. And so if my Tesla has, let's say, 80 kilowatt hours battery, how long would that take to charge? Pretty long time, right? You're talking on the order of what, times 5, like 400 hours. Yeah, so it's not even like beyond the sort of concept of it, if you kind of think about it from a sort of just a back of the envelope, like physics perspective, you just don't really get enough energy. Yeah.
400 hours divided by 24 hours is around 2 weeks. And maybe that's about the time it'll take to bring the battery.
Yeah, okay, wait, it's 2 weeks of like direct sunlight, right? So it's like also you're probably dividing, so this efficiency will get a lot worse. Because 20% is like if you are tilting the solar panel directly to be perpendicular with the sunlight, and then plus the sun doesn't always shine. So let's say you get like 6 hours on a good day and assume that your solar panels can like move and track with the sun, right? And then it's 2 weeks times 6, or sorry, times 4, 2 weeks times 4. So it'd take 2 months to charge your vehicle fully one time. So it's not, this is why this doesn't really happen. Yeah, yeah.
You need solar panels to be able to work efficient so that we're not gonna be feasible.
Yeah, yeah. That's a, you know, that's a sort of separate issue, but solar panels, yeah, I mean, they've come a long way, but sort of the nature of how they work, it's difficult to get them much more efficient than this. Hopefully that answers your question. Sweet, okay. All right, let's go ahead. Other components of this. So one of the big areas of efficiency benefit that you get from electric vehicles is through regenerative braking. Okay, and so we had talked about this a little bit, but essentially, when we're talking about electric vehicles where you have a battery going to this controller that that provides electricity into the motor, right? So motors take in electricity and produce kinetic energy through mechanical rotation, right? You can, as I was saying, motors and generators are exactly the same thing in reverse, okay? And so I can turn this motor into a generator. I should just relabel this into the generator, but I guess it's because this piece is the actual motor. But essentially, you are going in reverse where you're taking the rotational wheels, or sorry, the rotational energy from your wheels, and leveraging that in your motor slash generator. And so instead of using electricity to cause it to spin, you're using the spinning to generate electricity. That electricity can then go back and charge your battery. So that's the basic principle for regenerative braking, which has been around since the 2000s, the early 2000s in regular hybrids. And so that technology is pretty well developed and easy to implement, or relatively easy to implement for electric vehicles. And again, this is the aspect that really helps with higher efficiency in types of driving where you are doing lots of braking, essentially. The other nice thing about this that I'll say is that when you have electricity sort of going into the motor, or sorry, when you have rotational energy going into the motor to produce electricity, that creates resistance physically, right? That's how you're sort of going from moving to sort of stopping. And that resistance comes from the generator slash motor itself. And that's different from how we traditionally stop the vehicle, which is through either your sort of disc brakes or your drum brakes, right? Where you are essentially clamping down on something to make these stop spinning, generate friction to slow down, and you lose that energy as heat. So what that means is that when you are doing this regenerative braking, you don't need to do that, which means the lifetime of your brakes, of your braking system in electric vehicles actually lasts way longer than for your gas car. So in a gas car, you have to change your brakes every sort of X number of miles, right? And for EVs, that number can be, your brakes can last 2 or 3 times as long, right? And so that's a couple $1,000s of savings there. All right, why don't we take a quick break? Yeah, let's reconvene in 5 minutes. So the next thing that we'll talk about is about the last question, I believe, on our poll. So torque. This is Ford Mustang and the Mach-E. And if you look this up in Google, right, it'll give you sort of different ratings for the torque. Okay, so what we'll say about the torque is that the way in which gas cars and electric vehicles sort of leverage torque are a little bit different. And so, yeah, you can have higher torque ratings for gas cars than in electric vehicles, but the way in which it actually gets used is going to be slightly different and will lead to sort of different performance outcomes in the vehicle. So you may have heard that like EVs accelerate faster than gas cars on average, which is true, but that doesn't necessarily mean that their torque is higher. Okay, so let's talk about what is torque. So if you remember from physics, right, torque is the sort of, in a vehicle, the torque would be the force subjected at the sort of drive shaft. And we commonly, well, that's one type of torque. So if you remember from physics, this is expressed as, torque is expressed as force times distance. There is a little bit of nuance there, right? It might be sort of at a sort of different angle, so you have to take that into account. But generally, torque describes the physical sensation of torque is kind of like the jerkiness that you feel when you accelerate the vehicle. So this like sensation of being pushed into your seat, right? And so this is a graph of the instantaneous torque that you see for a gas car sort of at a single cylinder. Looks something like this. And that's sort of depending on the sort of position of your crankshaft. And right, so what's happening here, right? This is that power stroke, right? That is sort of exerting force onto the crankshaft. Okay, and so, right, the torque measures this kind of this sort of force that's being exerted by the engine into sort of different parts of the car. But it is a function, right, of distance. And so you can imagine, like I could describe a value of torque coming out right out of that single piston or sort of out of the engine to the crankshaft. And that would refer to the torque that you would be able to measure sort of right at the engine. But you can also measure the torque along sort of your drive shaft all the way to your wheels. And so that's also sort of a common place where you can report the torque. And so the torque values at your wheels will be different than the torque values that you see sort of at the engine. So that's just one thing to keep in mind when you look at sort of the torque values. And so the torque at the wheels are typically going to be higher, right? Because your distances are larger. All right, any questions about that? Okay, so let's look at the torque for gas cars. So they are somewhat related, the power of your engine versus the torque, but they're not the same thing. And so at some sort of power level, you will always be able to sort of get to some speed that is directly related to the power of the engine. But the torque is going to kind of describe metrics that are more associated with kind of the acceleration, right? And so you could have a vehicle with two vehicles with the same power that will both have the same top speed, okay? But the torque, but if you have different torques, the way in which they reach that top speed will be different. One of the things that you'll notice is this sort of particular pattern here, and that you can see that in this chart as well, which is looking at the wheel torque of a gas car in sort of different gears, okay? And so as your engine speed increases, your torque kind of goes up, and then at some point it will sort of plateau and start to come back down a little bit. And the reason why this happens, right, you can imagine that my ability to sort of instantaneously extract all the power out of my engine is dependent on the way that the engine operates, right? And so as you push down on your gas pedal, we go back to this guy, right? The sort of power stroke for one cylinder has to take a little bit of time to build up. And it's not going to be aligned across all of your sort of pistons, right? They happen at sort of different points in time. And then you have sort of lots of sort of frictional losses that are happening. And all of these things sort of compound with each other to help sort of produce this shape that you see, where you need to get your engine spinning up to some speed before you can sort of maximally get all of the torque out of it. Okay. And that's going to be pretty different for electric cars. So, okay, like I was saying, this is a similar type of thing. Torque across, now it's across the actual vehicle speed as opposed to the RPMs of the vehicle. But it takes time for pistons to go through the thermodynamic cycle, and due to sort of inherent losses of friction, you have this sort of shape. So unlike gas cars, as I press down on the pedal, right, I can basically send electricity through the motor at any rate that I want, right? And so I have full access to the torque that can be generated from the motor, even at a sort of zero speed. And because of that, you are typically going to have sort of much faster acceleration out of electric vehicles than you are out of gas cars. And so you can see the torque starts here at the top and then starts to full out sort of later. And that has to do with some of the effects of motor operation at higher speed that I was talking about before. Yeah, and so if folks have ever driven EVs or have ridden in EVs, you'll notice that they're sort of way zippier, right? And that's because of this exact sort of phenomenon. This is also the reason that a lot of like racing cars are starting to switch to electric or a combined version, like a plug-in type hybrid, because from a performance perspective, this is allowing them to accelerate very quickly as well. Yeah.
So for one thing I had a question about was, so obviously in a gas car,
Mhm.
get max torque, you gotta use more gas. So an electric car, surely it's the same. Like, do you have any insight on the relationship between maxing out your gas pedal, I guess your pedal in a EV?
Yeah.
How that drains the battery?
Yeah, it's the same thing. You will be, it's the same principle. There is kind of a optimal point from an efficiency standpoint to operate the motor. Typically, so from a speed perspective, so I'm not talking about acceleration here. From a speed perspective, it's sort of around like 20 to 30 miles per hour, whereas for gas cars, from a speed perspective, it's usually like 40 to 55 miles per hour for the most efficient. Okay, but I'm not quite answering your question because I think it's slightly different. It's like if you stomp down on the pedal, it's the same principle. You're operating the motor less efficiently, so you'll be draining the battery sort of faster for the same kind of distances if you're kind of stepping on the pedal. Yeah, I don't have like a exact kind of like metric to kind of describe that because it also depends on the motor of the vehicle. Yeah, exactly. So the reason why it's less efficient is because there's kind of an optimal operating condition for the motor or for the engine. And when you sort of go all out, you are not operating in that range and you use more energy. All right. So the last thing we'll talk about are plug-in hybrid electric vehicle drivetrains. So as I was saying before, this is by far the most complex, right? We have to have both components of gas cars and full electric cars. So you've got your engine and your motor, you've got your fuel tank and your battery pack. And then all the sort of moving parts that you have with the engine are in there as well. So you also have like this transmission system. Yeah, and so when we think about, oh, how does that work, right? You have both a motor and an engine. Do they like both spin the wheels at the same time? And like physically, how would that work, right? Because the motor is spinning at some speed and then your engine is operating at some speed that will cause the rotation to be probably at a different rate than what your motor is. So there's some sort of physical or mechanical complexities to this system that are a little bit sort of less straightforward. So let me describe a sort of generalized set of configurations of your drivetrain for plug-in hybrids. So you have a series, a parallel, and a series parallel. So in the series, the engine is powering a generator, right? So remember, what does that mean? The engine creates mechanical rotation. So we're causing something to spin, and you use that to power a generator. You use the rotational energy to produce electricity. That electricity will then go into charging your battery. The battery then operates your motor, which spin your wheels. And so from a mechanical perspective, the engine is not directly connected to the spinning of the wheels like it is in a traditional gas car. It is only connected through providing energy into the battery. And then this system here is what rotates your wheels. So that is in contrast to a parallel configuration where you can have your battery providing electricity to a motor, which directly affects the drivetrain, or your engine can also directly connect to the drivetrain. And then these two guys are not connected, right? And then the last one, which is probably the sort of most common, is the series parallel, where you have an engine which powers a generator. And that generator can then go through a transmission system to match the sort of rotational speed of your motor, and then operate through the motor to power the drivetrain. Or the generator can provide electricity into the battery, which then powers the motor. And so this might be something like, if you're driving on the freeway, and you're kind of like coasting, your engine's on and maybe it's providing energy into the battery, but then you hit the gas pedal, and then it can switch to basically put more power into the motor to accelerate your vehicle faster. And so in this case, right, the engine can sort of directly operate the drivetrain, or it can power the battery. Yeah.
So for everyone who know what this is like, you said you have to have, as you can see, you have to have components of both.
Yes.
So
And more.
The weight of that. How is it like? Is there? It doesn't sound feasible when you think about the weight having the weight.
Yeah. So the heaviest thing in the drivetrain, what was the heaviest thing that I said before? The battery. Yes. So that's actually the reason why the battery sizes for plug-in hybrids are typically way smaller. So the longest range batteries for PHEVs these days is like 50 miles, which is like 15 to 18 kilowatt hours ish. And so it's, 4, 5, 6 times smaller than a full battery electric vehicle. And that's where a lot of the weight is going to be sort of saved. Because yes, you do have these other parts, right? The motor, the transmission and everything, but the battery is really, really the heavy thing. Yeah, a good question. So some examples of these guys. So the i3 Rex, which stands for range extender, is kind of the canonical example of the series. So basically, you can think of this guy as basically just a full-on gas car, or sorry, full-on electric car, not a gas car. And then it's got this dinky little engine that powers a generator, and that generator will then sort of charge up the battery in this vehicle. And it's not so black and white where it's just purely series and parallel. There's some kind of in between. You can see here the power converter kind of can help power the motor, but generally this is the way that you think of this. So the sort of generator in this vehicle is not really, it's not really a sort of a traditional sort of gas engine drivetrain where you can just like continue driving it until your fuel tank is empty. This is really meant to extend the range of your battery by allowing the engine to sort of charge it. And the engine is not sort of directly powering the drivetrain of this vehicle. Yeah, as far as I know, the i3, I think, is the only one who is doing this. I don't even know if the i3 Rex is still being sold, but this system is not as common. Yeah. Yes, it does. Yes. Oh, it can, but it's pretty inefficient to do that. And really, the essentially, most people think of this whole thing here as just like having a kind of backup battery on board your car. Yeah. Good. Yeah, good question. Yeah, we'll talk about efficiency, I think next class or maybe next week. But for gas cars, yeah, this is important to mention now, I guess. The blowing up gasoline combustion, you lose the most energy by far, like compared to like all other parts of your drivetrain. So if we talk about electric cars, let me go to this chart here. Yeah, so when we talk about energy efficiency, we talk about energy going in and energy going out. So energy going in, like here, energy going in. So you lose a little bit of energy on the onboard charger. It goes into your battery pack. And then, right, the way batteries work, right, with the exchange of ions, you lose a little bit of energy there. You lose a little bit of energy in your converter. And then you lose a little bit of energy in the motor. To give you a sense of how much you're losing, each of these is going to probably lose like on the order of like a couple %. So through this whole system, you're talking about 90 to 95+% efficiency. And then, all of that will get translated into, movement of your vehicle. In a gas car, you have your input from gasoline going through the engine, and then the engine moves, or your engine has energy going into your transmission, into the drive shaft. And the engine, when it combusts the fuel, loses about, let's say, roughly 80% of the energy.
How many kilowatt-hours they like to charge battery, how much energy that
Yes. So basically you're talking about okay, over here. Yeah, if you went just through here, yeah, so really roughly speaking, I'm gonna say if you've got 100 kilowatt-hours of gasoline in your fuel tank, that will end up producing like 15 kilowatt-hours-ish into your battery. Yeah, so the big loss, right? Think about it like efficiency. Where are you losing all that energy when you combust the gasoline? Heat, right? There's a lot of energy and heat that's getting lost. And so that's why engines are really sort of relatively inefficient. You're talking on the order of like 20–25% efficiency, because you lose a lot of the energy from the combustion process to heat. Yeah, so electric vehicles, and we're going to talk about this a little bit more. Electric vehicles are way more efficient than electric cars when you think about the input and output at the vehicle level, okay? Because you don't have these kind of losses. You're talking about 1, 2, 3% losses for all the converters and the controllers and through the battery and all of that. It's not, so in my mind, I would say that's not necessarily the sort of fairest comparison, because yeah, there is. Yeah, there is. Actually, when you're operating the battery, for example, they can get pretty hot. So you need like heating and cooling systems. So that's going to take a couple %, but nothing close to a gas car. But this electricity all comes from something. And the biggest loss in that system is the initial combustion of fossil fuel to produce electricity. Okay. So I almost think of it analogously as like when you are burning coal or natural gas to produce electricity, that's kind of the equivalent of burning gasoline in your engine. You get a lot of loss in heat. But a coal plant, the turbine in a coal plant and the turbine in a natural gas plant is still quite a bit more efficient than the gasoline engine. And so the losses over the whole sort of life cycle will still be more efficient for the electric vehicle, but not as much as a lot of people say when they're just comparing the sort of vehicle.
So I guess ideally you want to talk about the inside line also.
Yeah. And we'll get into all the sort of implications of all that upstream stuff, but this is kind of like a kind of teaser for you guys, or heads up. Yeah, we'll look at these sort of upstream comparisons later on. But yeah, it's comparatively for these plug-in hybrids, again, these are kind of backup types of things. Now, you know, we're talking about one particular metric of performance, which is efficiency. And from an efficiency standpoint, like this would be terrible, but there are other reasons why people do this, right? Like, especially in the sort of earlier days of electric vehicles, people are worried about the range. The i3 only had like an 80-mile range for the first sort of set of models. So it's like, okay, what if I need to go further on a certain trip? You know, that's why plug-in hybrids are appealing for people, is that you don't need to worry about the range because you have these sort of backups systems. You can still use gasoline if you absolutely need to. Okay, for the Chevy Volt, you've got this sort of complex system here. So this is a sort of parallel series hybrid where your engine can operate actually kind of through the motor, and then it uses this planetary gear system. This is what I was talking about before, where you have things that are rotating at different speeds. You can use a planetary gear mechanism to translate that to sort of one speed for the wheels. So the way this works is there's an outer ring and there's an inner ring. So the outer ring would be sort of being powered by your engine. The inner ring gets powered by the big electric motor. And then the planetary ring, which is this blue thing in the middle, is the thing that's spinning the wheels. So everything can operate sort of simultaneously. So you can see, you know, we're not getting in, again, we're not going to get into sort of the mechanical engineering sort of nuances of these systems. But the idea, right, is that there's a lot of complexity that goes into these systems that allow you to do these combinations of having both your gas engine operate at the same time as an electric motor. These are, you know, really finely tuned, complex engineering systems that have been developed to allow for these things to happen. And this is all pretty novel, right? This isn't the type of thing that you would really see coming out of sort of traditional gasoline cars. And so a lot of this technology is getting developed specifically for these new plug-in hybrids. And different automakers are experimenting with different things, right? This is really, really different system from what the BMW, you know, i3 range extender was doing. These are very different systems. And so, you know, everyone's kind of on the learning curve right now for kind of what's the best way to do this. And frankly speaking, I think a lot of automakers were initially kind of really going in this direction because they were worried about sort of consumer acceptance of full battery electric vehicles, and plug-in hybrids really act as this sort of transition technology between them. But it seems like the demand is there for full battery electric vehicles, right? And so we've definitely seen, I would say in the recent years, a bigger movement towards full battery electric vehicles than kind of producing these systems, right? The Chevy Volt is no longer a thing. The Honda Clarity is also no longer a thing. And those were the two sort of best-selling plug-in hybrids for quite a while. Okay, and so, as I was talking about with a lot of these technologies, even with the like motors, for example, a lot of the technologies related to the powertrain have really been recently developed over the last decade, and they're continuing to improve. We've already seen lots of innovations in motor technology, but basically more power, higher efficiency, better control systems can help improve efficiency. And then even battery attributes that can decrease weight, increase energy and power density, all of these things will help with efficiency of the vehicle. Yeah, and so I think that over the next decade, we're going to continue to see lots of improvements that will improve efficiency, lower costs, and all of these things are going to help sort of continue to make EVs sort of more accessible to the rest of the population. Okay, so with that, we are finished for today.